Hey everybody, welcome back for limits day 2. Today we are going to calculate our limits algebraically. So we no longer have a graph, and we're going to use some direct substitution methods here to calculate these. So we're always going to use direct substitution to evaluate algebraically, and that means that we just take the x value of the limit and we plug that into our function. So two things could possibly happen here. We could evaluate without any issues, and we could get a value that our limit is equal to. All right, the second option is that you could get a 0 in the denominator, or an indeterminate form, which is 0 over 0. Okay, and if that happens, it means that the problem is not over. That means we have to use some sort of algebra techniques, perhaps factoring, and we want to cancel out and simplify our function to see if we can then plug it back in and maybe get a different value. So I just want to check first that you can substitute in without having to do any extra work. All right, so here is a very easy first example. This is the limit as x approaches 2. Okay, so we want to plug it in and see, do we get an answer? Okay, and we do. We get an actual concrete number. So that means that the limit here as x approaches 2 for f of x equals 1. Okay, and that was my final answer, and that is much easier than looking at a graph. Okay, we're going to do the same thing on example 2. So now we are approaching -1. Okay, we can plug that in, and we're going to evaluate this equals 2. Concrete number, no problems. So the limit as x approaches -1 for this function equals 2. Could not be any easier for these two first examples. Okay, so now functions are a little bit more complicated, but we're still going to follow the same method. Okay. So we get 5 over 16. Okay, even though it's a fraction, that's a fine number. Okay, and again, one more, plug this in. Okay, so we're really doing 1 to the 100th, which equals 1. So okay, so we see that this direct substitution method does work. Now, if we were to do that again, and we get something like 0 over 0. Remember, that means the problem is not done, and we should now think about trying to simplify. So I could factor this, and I'd have a new simplified function, and I know that that means there's a hole at x equals 4. Well, that makes sense as to why I was getting 0 over 0, which is technically undefined. That's why it's not working. So what happens as the function gets closer and closer to 4 here? So we're going to use our simplified version, and if we plug in and use direct substitution now, it's going to tell me that my function is approaching 1 over 8. So the limit as x approaches 4. All right, so previously we needed the graph to see that there was a hole and to approach this to get the limit. But now, if we simplify before doing our direct substitution, it provides the limit when you have it, when the limit is at an undefined value like x equals 4 for this one. Okay, so I'm going to start off my problems now by factoring. Okay, so I'm simplifying my function. Okay, so remember, we're always evaluating limits algebraically into the simplified function. So I see here, because I canceled this out, I know that there's a hole at x equals -4. And remember, when we did these algebraically, that the limit can equal a hole. The function can't be evaluated at it, but the limit can approach the hole. And this is how we algebraically determine what it's approaching. Okay, so now I'm going to use my direct substitution. So the limit as x approaches -4 equals 2. So you cannot leave it as an indeterminate form, as 0 over 0. Now there's going to be other situations involving 0, okay, but they are not considered indeterminate. Indeterminate is a 0 on the top and the bottom. All right, so why don't you pause your video and try and do each one of these, and then come back in and check your answer. All right, so I'm factoring and getting a simplified function here. And then I can do direct substitution. So my limit as x approaches 3 equals 2/3. Okay, and in the second example, these are monomials, so I'm actually going to simplify those. Cancel the one on the bottom with one of the ones on top, so I'm left with a 2x. So now when I direct substitution here, and I get 0, that's fine, because it's not 0 over 0. So the limit as x approaches 0 for this function equals 0. Right? That's different from the indeterminate form. Okay, so again, now that we know, I always just factor to begin with. So 1 over x plus 5. All right, so we want to find the limit as x approaches 5. So use your simplified function. So 1 over 5 plus 5. All right, so I get an answer for that one. So the limit as x approaches 5 is 1/10. And the limit as x approaches -5 Okay, so this is another situation dealing with 0, but this is not indeterminate. It is not indeterminate because the numerator is a number. Indeterminate form is 0 over 0. So this situation, okay, my direct substitution has produced something that's undefined, right? If you tried to evaluate that. So an undefined direct substitution means that the limit does not exist. So that's telling me that if we graphically found the limit from the left and the limit from the right, that they would be approaching two different values. Okay, and if you want to grab your grapher and check, if you put 1 over x plus 5, you will see just that. Okay, and that's essentially what is happening. Okay, when you get a undefined, you get does not exist. Okay, one side of the function is approaching negative infinity, and the other side is approaching positive infinity. Okay, there's one more thing that we want to look at here today, and that is piecewise functions. Okay, so when you're given a piecewise, you have to manually check each one-sided limit. So when we were just doing all these direct substitutions algebraically, that automatically takes care of the two-sided limit, except for piecewise, because piecewise now has two different functions, and one of those is actually going to represent the limit from the left, and the other one is going to represent the limit from the right. So if I'm trying to find the limit as x approaches 3 for this function, well, whenever x is less than 3, that's the left side of the graph. So that has to be the left-sided limit. And if it's greater than 3, that has to be the right-sided limit. So I want to check each one of these. Okay, and so what is really happening here? This is telling me that my limit from the left approaches 4, and my limit from the right approaches 10. Well, remember, for the two-sided limit to exist, they have to come to the same number. So this limit does not exist then. Each one-sided limit does, but that's not what we're looking for. Okay, we'll try one more of these. So when x is less than or equal to 6, this is the limit from the left, and greater than is going to be from the right. Okay, so we have to evaluate each one individually. Okay, and again, they do not approach the same number. The left side goes to 8 and the right side goes to 11. So it does not exist. Okay, so that is everything that we need to know here for evaluating limits algebraically. Please make sure you have all of these examples down, and any questions that you have are included in your notes so that we can take care of those during our next class. All right, thank you guys so much for watching, and I will see you later.